Hi, welcome back to Statics 1. And today we're going to talk about a particular type of problem where we have a force along a line. We know the magnitude of the force, and we want to write that force as a vector. So I'm going to write here the concept, which is forces along a line. And the challenge is to write these as a force vector in the Cartesian form, forces along the line. Okay, so let me show you kind of an example. And this is actually an example from later in the book where we're dealing with moments. But in this case, and it's in 3D, where should I do it? I'll put it over here. So it's in 3D, so we're going to have our we have our x direction, our y direction, and z vertically. And at the origin, we have a tree. So I'm going to put branches on this tree. And we have a tractor over here, and it's pulling. Here's our tractor, and I'll put wheels on it here. Well, do the best we can. And we're going to call this point B, where we attach a cable, and it'll have coordinates of bx, comma, by, comma, bz. In this case, bz would, be, of course, be 0. And we have a cable that goes from B to A. Somewhere here on the tree, they've attached a cable. Let's see if I can get this. Actually, let's try this in a different color. Draw this in pink. And here's our vector going from A to B. Straight line. Ah, perfect. All right, here's my vector. And I'm going to call that force vector AB. So we put a arrow over it because, of course, it is a vector. And here I'm putting my point A. And, of course, we had B here. And A would have coordinates AX, AY, and AZ. So how are we going to find this force vector if we say we now know the coordinates of the A point, the B point, and we know the magnitude of the force vector? So that's the challenge. And it's really pretty simple four-step process. And the first part is to find the position vector between these 2 points. And I'm going to call it RAB, as we talked about it last time in our previous lecture. So it's the position vector R going from A to B. Okay, so that's a position vector. Remember, that'll have units of length. In this case, it may be like meters or feet. And then the second step is to find the magnitude of RAB. Magnitude of our position vector, RAB. And that magnitude is, which I'll just call RAB. So find magnitude of our position vector, RAB, comma, and RAB. So here's what we're looking for. And that's just equal. We're going to find that using the Pythagorean theorem. So I'm not even going to write that down. We know that's the square root of the sum of the squares of the distance. And so the magnitude of RAB is simply the distance between A and B. Distance between A and B. All right, third step in our process is to determine a unit vector in the direction from A to B. So we're going to find a unit vector UAB right here, and I'll put in parentheses a unit vector. And we should know, because we just talked about this previously, that unit vector UAB is simply equal to our position vector AB, RAB, divided by the magnitude of AB, or the distance between A and B. And the fourth step and the last step is simply to find our force vector. And to find the force vector, so we know we know a unit vector basically. I'll draw it on here. So if we have a unit vector, I'll do it in green. Here's our unit vector here. And it basically has a magnitude of 1. So to find the force vector in that direction, all we need to do is to multiply our unit vector, AB, times the magnitude of our force vector, FAB. So that's actually it. That's our fourth step. Let me write that down. So we're going to find the force vector. And this is what we were looking for, of course. The vector directed along that line, AB, equals our unit vector times the force, the magnitude of our force vector. And let me put that here, just so we remember. This is a magnitude of a force vector, and it would just be like the number of kilonewtons, or number of pounds. So let's look at this example here, and I'll actually put some numbers in it, and we will solve for the values, just so you can have an example. And this is an example actually from a later chapter where we're dealing with moments. So let's say, in this case, that the force AB, let me separate that. So the magnitude of my force AB equals 2 kilonewtons. Notice no arrow because it's magnitude. And I'm going to say that AZ equals 12 meters. And BX equals 4 meters. And BY equals 12 meters. Everything else is 0. So, for example, B sub Z equals 0 because we're basically on the plane, on the XY plane. And in this case, we're at the origin, so AX and AY are all equal to 0. Okay, so we don't need to define those. So let's follow our four-step process and see if we can find our force vector AB along this line that describes how the force that the tractor is pulling on the tree. All right, so what is our position vector? So RAB, simply enough, and I think we can basically see that we're going from the origin to a BX and BY. So RAB equals BX, which is 4 meters, times I, plus BY, which is 12 meters, times J. And then we have minus, because we're going from 12 down to 0. So it's like 0 minus 12 times K. So minus 12 meters times K. That's our position vector. Step 1, accomplished. Find the magnitude of RAB. So we'll do that next. RAB equals square root of 4 meters squared plus 12 meters squared plus 12 meters squared, right? Pythagorean rule in 3 dimensions, and it's going to be equal to 17.4356. And notice I keep extra significant digits because this is a kind of a transient result that we want to keep, and then we want to make sure our final solution is as accurate as possible, although we will end up rounding that off to 3 significant digits, like we usually do. All right, step 3, finding our unit vector, AB, and it's just equal to the unit vector divided by its magnitude. So we're going to take this result, our unit vector, and we're going to divide it by 17.4356. So we get 3. So here we are, step 3. Here's our unit vector, AB, equals, and I'll write it, how will I do this? I'll write it this way, it'll be a little bit, save myself a little bit of writing, 17.4356 meters times 4 meters I plus 12 meters J minus 12 meters K. And so basically this can distribute across each of our terms, and we end up with the result of 0.2294 I plus I vector 0.688. Sorry, I'm getting a little messy here. 2 times J unit vector minus 0.688 K, again a unit vector. Okay, so that's my unit vector. So we've done step 3, right? We found our position vector, RAB. We found the magnitude of RAB. We divided them, the position vector by the magnitude to find the unit vector. And now we're going to come up with the final result, step 4, where we're going to take this UAB and we're going to multiply it by 2 kilonewtons. And notice the unit vector has no units because we've essentially taken meters divided by meters. And so it has no units. And so in the final result, which is FAB, and I'm running out of space, so I'm not going to write everything here, but I'm going to write UAB. I'll just write this 2 kilonewtons times UAB. And then I'll write out the result here, which is 0.459 I minus, plus 1.376 J unit vector minus, hopefully this is not going to end up getting cut off. Am I down here? I think it is. I'm going to put it here, minus 1.376 K. Okay, in the indicator. So here's our result. This is the result we were looking for. It's the force that the tractor is exerting along this cable on the tree. Okay, so that's the final result we're looking for. The next thing we're going to be doing is dealing with dot products. And if you have any questions on this, bring those to class or email me them, and we'll talk about it, and I will see you in class.